welcome to the lecture series on differential equations for undergraduate students. Today's lecture is on ADI method for Laplace and Poisson equations. We are learning the numerical methods to solve the Laplace and Poisson equation. In the last lecture we had learned a numerical method to solve the Laplace equation del 2u over del x2 plus del 2u over del y2 is equal to 0 using a 5-point discretization formulation as 1 1 minus 4 1 1 u is equal to 0, and similarly for Poisson equation del 2 u over del x2 plus del 2 u over del y2 is equal to f x y. We can discretize again using the same kind of discretization 1 1 minus 4 1 1 u is equal to h square times f x y. We do know that this by this discretization method, when we have use this difference quotient to change this partial derivatives to the difference quotient, we have got a matrix, or we have actually arrived with algebraic equations where the coefficient matrix was very sparse, and in that case we had find it out that the Gauss elimination method was not a very suitable method for that one, because the matrix is very large and it is sparse. So, we have learned that as iterative methods would be better, and in the last lecture we had learned about one iterative method called Gauss-Seidel method, which at the older times was also known as Liebman's method. Today we will learn about one more iterative method. Let us start with the same discretization scheme. We do have one more term. A matrix is called tridiagonal if it is all non-zero entries are in the main diagonal and in the sloping parallels immediately below and above. Say for example, this matrix is a tridiagonal. What we are having is one main diagonal, then it is immediately below diagonal, and then it is immediately above diagonal, and all remaining entries in this matrix are 0. Since we are getting is that our coefficient matrix in this numerical method as a sparse matrix, that is having many zeros, and we are finding it out that we are placing those zeros at different places, and that is why we had used this Gauss-Seidel method rather than the Gauss elimination method. Now, the question is coming in this Laplace equation or in solving this Dirichlet problem for Laplace or Poisson equation, when we are using this 5-point discretization formula for the difference quotient, can we change our matrix coefficient matrix to the tridiagonal kind of thing, because what is happening is in the tridiagonal one, if we can change our matrix to this form, in this form this Gauss elimination method can be used, and it would be very simple. Since we have got that in iterative methods we have to apply many iterations and then we have to come to the solution. So, in the Gauss elimination at one stage we could get the exact solution actually. Certainly, if we are saying is that could we change it out, of course we can change it out, but the method would be again iterative. So, the answer to this, that can we change our coefficient matrix or can we formulate this Dirichlet problem for Laplace equation in such a manner that coefficient matrix is a tridiagonal matrix? The answer is yes, and a popular method of this kind is known as ADI method. Now, what is this ADI method? ADI method, its name is actually alternating direction implicit method. The name says is alternating direction implicit method, that is it is not very it is not explicit, that is it would be using implicit means is that we have to use iteration, because both the way we would be getting the unknown ones. So, the 5-point approximation formula for Laplace equation we do know is this 1 1 minus 4 1 1 is u is equal to 0, that is if I am talking about this point u I j, then it would be u I minus 1 j, this would be u I plus 1 j, this would be u I j minus 1, and this would be u I j plus 1. So, this was the formula, if you do remember, that is in this manner we were moving, that is starting from here u I plus 1 j plus u I minus u I j minus 1 u I minus 1 j minus 4 u I j plus u I j plus 1 u is equal to 0, that is what the Laplace equation formula we have got it. So, this is what we were having this discretization formula at the point uij, and similarly for every uij we do write this equation, that this difference coefficient, and then we do get the discretization of our Laplace equation. Now, can we change it? Now, that is, we want it to be the tridiagonal. You see, tridiagonal means is I want diagonal elements over here, then one element over here and one element over here. Of course, certainly as I said is we could do it. Let us see how we are doing this. Now, let us rewrite this as ui minus 1j minus 4 uij plus ui plus 1j. So, what we are having is ui minus 1j, uij and ui plus 1j. This is at the left hand side, and the right hand side is the terms are uij minus 1 minus uij plus 1. So, now you see we are getting this row, this jth row, this fixed row j is common, j is fixed one. So, this jth row on the left hand side, and the right hand side we are having is that ith column. Of course, we can rewrite in another manner, that is we can rewrite this as that ith column on the left and the jth row on the right. So, like this one, if I am writing it uij minus 1 minus 4 uij plus uij plus 1 is equal to minus ui minus 1j minus ui plus 1j. So, what we are rewriting this equation, this 5 point formula into this form, where either I am writing it as the left hand side as the jth row and the right hand side the remaining ith column, or the left hand side is the ith column and the right hand side is the remaining jth row. Now, in this what we are getting is, that is we are getting uij's on both the sides, while here we were having is the right hand side was the 0, or if it is a Poisson equation we would be having some known terms over here, while here we are having both the sides uij. That is why we are calling it implicit, and you are seeing is that is either I can write it as a jth row or I can write it as ith column kind of thing. So, this would be we would be alternating the method. What is this method actually? Method is also that iterative method. What we do is, given any Dirichlet problem, again we would discretize it, that is make the mesh and this grid and get the mesh points, and each mesh point we use that arbitrary starting value. That is, because it is an iterative method, we start with arbitrary starting values. So, uij 0 we would take some values and then compute the new approximation of u at all mesh points in each iteration. That is, again it is iterative. At each iteration we would compute at each of these mesh points, we would calculate this new approximation. How we are approximating it? We would be doing is, in the one iteration we use the formula for row, that is for fixed jth row we would use this formula, and in the next iteration we will use the formula for that ith column. That is what we are altering the direction. Once we are moving to the row and then we are moving to the column. So, we are altering the direction. How we are doing it? Let us say, let at mth iteration we computed the approximation for ijth element as uijm, that is at ijth mesh point. We have calculated it as uijm. Then what we will do to get m plus first approximation? What we do, we will use the jth row formula, that is for fixed row j we would use the formula. So, from here if we are moving, we do say is, that is we would get this formula. What we will do, we will substitute the mth approximation to the right side, and the left side we say is that we would be getting the m plus 1 values, that is in this manner we would be doing, substituting the mth approximation and right as this one. You say we do find out uijm plus 1 as ui minus 1j m plus 1 minus 4 uij m plus 1 plus ui plus 1j m plus 1 is equal to minus uij minus 1 m. Now, we have used this whatever we have got in the mth iteration, that approximation, that we would be substituting on the right hand side, and uij plus 1 m. This we will do for all for we are using for fixed rho j. So, if I am using this fixed rho j, we would go for all internal mesh points, all the mesh points, because at the boundary conditions, since we are talking about Dirichlet problem, that is the boundary values are being given, the boundary condition will give me the values at the mesh points at the boundary. So, those points we will not be talking, we will be talking about all internal points, and we will use, when we are using this formulation, certainly at certain points we would get the boundary points as well, and for that boundary points we will use the boundary conditions. Thus, what we would get, we will do it for each for all mesh points, internal mesh points for the rho j. So, let us say that is there are n points. In this manner, when we use the boundary condition as well all this, what we will get finally, we will get n algebraic equations in n unknowns. We solve this system by Gauss elimination method. This n algebraic equation in unknowns which we will get, there would be actually simple equations that we could solve by Gauss elimination method. So, that we do get the solution, exact solution at that time. Now, in this manner we will go for all rho j's, that is I would go for starting from j is equal to 1 to j is equal to n, how many this grid points, how many grids we have taken, that is how many rows we have taken, or for all those rows we would go. So, we will get m plus first approximation for all the internal points of the jth row, and then repeat these steps, that is from the fourth step, that is internal mesh point, what we are getting is that approximation, we will repeat all those points for all rows. Thus, we would get uij plus 1 for all uij's inside this area of interest. Then now, so we have got m plus first approximation. In the next step what we do, we alternate the direction, that is now what we will go in the next iteration, we will alternate the direction to get the next approximation uij m plus 2. So, what we will use? We will use the formula for fixed column I, uij minus 1 minus 4 uij plus uij plus 1 is equal to minus ui minus 1j minus ui plus 1j. What we will do again? We will substitute the m plus first approximate values, whatever we have got the values over in this last iteration in the right hand side, and thus we would get the equation as uij minus 1 m plus 2 minus 4 uij m plus 2 plus uij plus 1 m plus 2 is minus ui minus 1j m plus 1 minus ui plus 1 j m plus 1, that is right hand side we had put the values of the m plus first approximate values, and we are trying to find out the m plus second approximation for uij's. Now, using this kind of one, here we would substitute those values and we will get the equation over here, certainly with boundary condition and all those things. So, what we would get, this we would do in all internal mesh points. So, let us say that is for column fixed column I, let us say there are m points, then what we would get? We will get again that is m algebraic equations in m unknowns. We can again solve them using the Gauss elimination, because what equation here we would get, that would be of this form of tridiagonal matrix actually, because we would be at each mesh point. If I am using this row fixed row, I would be getting only these 3 points, that is the point, its left hand point, its right hand point, and if I am using the column 1, we would be using the, we would be getting the point and its upper point and its lower point, that is all these 3 points we would get. So, like that if we are moving either in this manner or in this manner, we would simply get a tridiagonal matrix, and for that matrix we do get the solution using the Gauss elimination method. So, again solve this system also by the Gauss elimination method. I would get the approximation m plus second approximation uij m plus 2 for all those internal points of the ith column. Now, repeat this process of from 12 to 16 for all columns, so that I do get the approximation uij m plus 2 for all. In this manner we would be go on repeating till we get a nice solution. So, let us what the nice solution we do mean is, we do say is that when the two approximations are nearing each other, that is there is not much difference between the two approximations, that is say if I do have uij m plus 1 and uij m plus 2, the absolute difference between uij m plus 1 and uij m plus 2, if this is less than some very small number which we have prefixed, then we say is that we can stop the iteration. In this manner we are going to find it out. Let us do one example using this method, that is ADI method. We are going to do the same example. The 4 slides of a square plate with side 12 centimeter made of homogeneous material are kept at constant temperature 0 and 100 as shown in this figure. Using a grid of 4 centimeter and applying this ADI method, alternating direction implicit method, find the steady state temperature at the mesh points. So, we are having this boundary condition is giving that the temperature is being kept at the 3 sides at 100 degree centigrade and on the one side, that is on the upper side, as the 0 degree centigrade. We have to use this grid and mesh point, that is we would use this 4 centimeter, this total is 12 centimeter. So, we have to use this 3 cross 3 grid point. So, let us see what our problem is. You do remember that this is the same problem which we have done using this Gauss-Seidel method. So, the steady state heat flow equation is the Laplace equation that we do know, del 2 u over del x 2 plus del 2 u over del y 2 is equal to 0. Now, with the boundary conditions given as this, using this h is equal to 4, we have to find out the grid and mesh points. So, grid and mesh point will make on this region of interest, that is whatever the region we have been given, this is a square region. So, given problem is this, so we do get it a 3 cross 3 grid point. So, we say this is for each h is 4 from this side as well as on this side. All these mesh points, of course, it is 0 0 mesh point, this is 1 0, this is 2 0, because x is increasing in this way and y is increasing in this way. So, we are taking x as the first one and y as the second one. So, we do get here p 0 0, this is the point p 0 1, this is the point p 0 2, this point would be p 1 1 and so on. And the boundaries we do have, that is at u 0 0 it is 100, u 1 0 it would be 100, u 2 0 would be 100 and so on. In this side we do have is that is u 1 3 is 0, u 2 3 is 0 and say u 3 3 is 0. So, like this we do have this one. Now, we have to formulate our problem, that is we have to find out the difference, that is apply this alternating direction method. So, start from the step 1. We would have to have our initial guess. So, let us say the initial guess again as in the last one we had the 3 sides, the boundary condition is 100. So, again we are taking this initial guess as 100. Since we are having in this one this 4 internal points, all these other points are on the boundary, and for the boundary condition is given. So, we do know that u 0 0 has to be 100 here, u 1 0 has to be 100 here, similarly u 0 3 has to be 0, u 1 3 has to be 0 and so on. So, we do make it that is the 4 internal points only. So, u 1 1, u 2 1, u 1 2 and u 2 2, that is u 1 1, u 2 1, u 1 2 and u 2 2, these 4 points we are taking, and so we would get actually 2 rows and 2 columns, that is the points, and each row and each column we will have only 2 and 2. This is the problem we have taken, so that we can solve it here by hand without using any calculator or any calculating machines. So, this is initial guess we have taken as 100. Now, the first step is that is use the fixed row. So, first I am using the j row j, that is j is equal to 1, the first row. In the first row the first point is p 1 1, that is 0.11. Here we would like to write the equation. So, we would get u 1 1. So, u 0 1, do remember that is u I minus 1 j minus 4 u I j plus u I plus 1 j. So, my j is fixed as 1 and I is varying from 1 to, so I is also 1. I is also 1. So, I would get u 0 1 minus 4 u 1 1 at 1 plus u 2 1 at 1 is equal to minus u 1 0 minus u 1 2 0. Now, you are seeing it here in the scheme when I have described, I had used all the places m plus 1 and all the places as m. Here at certain places I am not using this m that is 0 or 1. Why? Let us see here. This is the point u 1 1. It is before point, that is we are talking about this fixed row. So, this 3 points we have to talk about. This is the point u 0 1. U 0 1 is the point at the boundary. This is it is known boundary condition. This is not an internal point. So, we are not using any initial guess. This we would use exactly what is the boundary condition. So, that is why this one we are not using. Similarly, when I go to the right hand side, this point and this point we have to consider. For this point, of course, we have taken the initial guess. For this point, we have to use the boundary condition, that is why this is not being used. Similarly, if I go for the second point, that is I is equal to 2 u 2 1. So, I do get it from here u 1 1, since this is internal point. So, 1 minus 4 u 2 1, this is also internal point, plus u 3 1, this is boundary condition, boundary point. So, we are taking it u 3 1 as such, minus u 2 0, this point, this is also a boundary point, minus u 2 2, this is internal point. So, initial guess 0. Now, this is for second I is equal to 2. Now, substitute the values, since we are taking is u 1 2 0, u 2 2 0, these are 100, u 1 2 0 and u 2 2 0, they are 100. The boundary condition u 0 1, u 0 1 means this point, u 0 1 is 100, then the other point is u 1 0, this point, this is also 100, and here the boundary point is u 3 1, u 3 1 means this point, this is also 100, and then u 2 0, this is the point, this is also 100. So, let us go one by one. The first one, minus 4 u 1 1 plus u 2 1 at 1 is equal to minus 100 minus 100, and this point also taken to this side minus 100. So, I have got minus 300. Similarly, here u 1 1 minus 4 u 2 1 is equal to, this is minus 100, this is minus 100, this point is also u 3 1 is this point, this is also 100. So, this side we are taking it is minus 300. So, we have got this equation now, minus 4 u 1 1 1 plus u 2 1 1 minus 300 upon u, and u 1 1 minus 4 u 2 1 is equal to minus 300. This is because we are having only 2 internal points here. So, we do get a system of 2 equations in 2 unknowns. The simple one, as I said, is we are doing it without any computing help. So, we are taking a small example. We can solve it using the simple method of Gauss elimination, that says is that the solution I would get in this manner. The first approximation u 1 1 at 1 is 100, and similarly u 2 1 at 1 is 100. You can solve it by yourself and see, it is very simple equation. So, we are getting it as a 100. Now, move to the row 2. Now, we have started, that is this process has to be repeated for all rows. So, the row 1 I have taken, now move to the row 2. Row 2, if I write this equation, so the first point, that is I is equal to 1, if I do take the point is p 1 2, that is we have to take u 1 2, that is here we would get it u 0 2 minus 4 u 1 2 plus u 2 2 is equal to minus u 1 1 minus u 1 3. Now, you see u 0 2, that is boundary point. So, we are not using any approximation, and u 1 3 is also boundary point. So, we are not using any point over there also, and u 1 2 we want the first approximation for u 1 2, and the right hand side u 1 1 we will use the initial approximation. Certainly, here we are not going to use any other thing. So, we have got now. Similarly, if I go for I is equal to 2, that means this point u 2 2 point, p 2 2 point. So, for that what we would get u 1 2 at 1 minus 4 times u 2 2 at 1 plus u 3 2, this is the boundary point, is equal to minus u 2 1, this is the internal point. So, it is 0 minus u 2 3, this is a boundary point, this is for I is equal to 2. Now, put the values for the first one u 0 2, u 0 2 means this point, this is 100, u 1 3, u13 means is this is the point which is 0. So, we are getting it 100, this is 0 and this is also 100. So, we do get is minus 4 u121 plus u221 is equal to minus 200. Similarly, in this one u3 we will be getting it the point u32. u32 point means is this is the point. Yeah, u32 is this point, that is 100, and then we would be getting it as the point u23. u23 is this point which is 0. So, again we would be getting it u11 u12 at 1 minus 4 u22 at 1 is equal to minus 200. Again we have got, because we are having 2 internal points only, the system of 2 equations in 2 unknowns, again simple one. The solution using the Gauss elimination method we do get is as u12 as 200 by 3 and u22 also as 200 by 3. So, we have got now the first approximation u11 as 100, u21 as 100, u12 as 66.667, u22 at 1 is 66.667. This is my first approximation. Now, we will move to the next step. So, move to the second step. So, first approximation is this one. From here we would move to the second step. For the second step, again what we have to do, we have to alternate the direction. Since we have done in the first step using the row, now we will move to the using the columns. So, for first I will take the column I is equal to 1. In this column I do have 2 internal points and 2 boundary points. So, I would start with the first point, that is j is equal to 1. Here if I write, because we are going to write it using the column. So, we just start from here u10 minus 4 u11 plus u12 is equal to minus u01 minus u21. Now, the point u10 and u01 are the boundary points, and the right hand side we do have u21 the point, this is internal point. So, the first approximation, and we want the second approximation. So, the left hand side we will take all those points as the internal points as the second approximation. So, this is my first point. Now, similarly move for the second point in this column, that is this u12, that is p12 point. So, for this we have to write using the column 1. So, we will go for u11 minus 4 u12 plus u13 minus u02 minus u22. Again these 2 points are your boundary points. So, those points we are writing as such, and this right hand side u22, this will take the first approximation and others we would write as the second approximation. So, this is for j is equal to 2. This one, now let us just write the points. Since we are getting is here u10, u10 means is this point says is 100, then u01 means is this point, this is also 100, and u21 in the initial one, that is first approximation, we had got it as 100. So, what we have got again is minus 300. Similarly, if I move here u13 means is we would be getting is this point, this is 0, and then we do have it our point here u02 means this point is 100, and the initial approximation u221 is 66 point this one. So, what we do get is, that is I am writing it as 200 by 3 actually. So, u11 minus 4 u12 is equal to minus 500 by 3, that is minus 200 by 100 minus 200 by 3. Now, if I solve this system of equations, so what we have got 2 internal points only on the column I, this first column. So, we have got 2 equations in 2 unknowns. The simple system we can solve it using again the simple Gauss elimination method. We do get is u11 as 820 by 9 or 91.11 and u12 as 580 by 9 is equal to 64.44. This is what we have done for the first column. Now move to this. Now we have to repeat this process for remaining columns. So the next column is the second column. So move to the column 2. Now for this again column 2 we do have two internal points. First we will move for I is equal to j is equal to 1, that is the first point, the point P21 that is corresponding to U21. We are moving in the direction of the column. So we will take U20 minus 4U21 plus U22 is equal to minus U11 minus U31. U31 and U20 these are your boundary points. So we are writing them as such. On the left hand side the second approximation, on the right hand side your U11 the point. So this is the first approximation. This is for your j is equal to 1. For j is equal to 2 the point is P22, that is for U22. For this again we are using this column method. So we would get U21 minus 4U22 plus U23 is equal to minus U12 minus U32. Now again U32 and your U23 they are the boundary points. So they are being kept as such. The right hand side U12 this is the first approximation, left hand side the internal points U21 and U22 we want second approximation. Now substitute the values. U20 is this boundary point which is 100, U31 is this boundary point which is also 100. So it is minus 200. U11 we at the first stage we have already got as minus 100. So the first equation would give me minus U21 plus U22 is equal to minus 300. Then U23 is this point which is 0 and U32 is 100. So minus 100. U12 at 1 we had already got minus 200 by 3. So minus 200 by 3 minus 100 we would get it minus 500 by 3. So my second equation gives me U21 minus 4U22 is equal to minus 500 by 3. Since there are two internal points only, two internal mesh points, we will get two equations in two unknowns. So this first equation, the second equation, two unknowns. Now simplify it, the solution we would get, the simplification you can do yourself. So this would be U21 we are getting is 820 by 9 as R as 91.11, U22 we are getting as 580 by 9 or 64.44. So what we have got the second approximation. Now that is for all four internal points we have got the approximation. The second approximation we have got U11 as well as U21 is 91.11 and U12 as well as U22 is your 64.4. So we are getting is that we are moving in the row manner, actually we are getting the same ones. Now we are getting is that is they are internal points. I am not going beyond the second approximation. This is just to explain you the typical step. So I had started with the initial guess and gone with the first step, that is the fixed row step, and then alternating the direction went to the column step. Now in this manner you can move on doing it till you do get that approximation stabilizes. Now here in this when we are doing this process, this approximation are depending upon what the initial guess we are starting, and certainly about that method. What this method is saying is the convergence of these methods we are not discussing in this first course actually. Now if I start with any other initial guess, how does it affect? Let us say the same example, here we had started with initial guess as 100, 100 and 100 for all 4 points. Now if I say I started initial guess without knowing anything, let us say is that initially all the points are 0, then what will happen? So let us do this same example with another initial guess as U11 is 0, U21 is 0, U12 is 0 and U22 is 0. So what this is my initial guess. First I will go with the fixed row, that is again I would like to go with the row 1. Row 1 means is I would have two internal points, I is equal to 1 that u11 and I is equal to 2 that u21. So, first for u11 I am going with the fixed row. So, for I is equal to 1 I would get u01 minus 4 u11 plus u21 is equal to minus u10 minus u12. That is again using the similar manner with this one for the last as we have just now done. So, for this is for I is equal to 1, and for u21 I would get it u11 minus 4 u21 plus u31 is equal to minus u20 minus u220. Now, we have the boundary conditions are same. So, here also we do get is 100 and here also 100, that is my u01 and u10 both are 100, but now my u120, this is we have taken initial guess as 0. So, my equation now would be, first equation would be minus 4 u11 plus u21 is equal to minus 200. Similarly, if I say in the second equation my boundary points u31 and u20 both are 100, but the initial guess u22 is 0. So, again I would get the equation as u11 minus 4 u21 is equal to minus 200. Now, solve these two, again we are getting is two internal points. So, two equation 2 unknown, the solution would be u11 is 200 by 3, u21 is also 200 by 3. So, we have got the different solution now, and now move to the second row. Second row means the points I would have u12 and u22. So, first for u12 we are moving in the row manner. So, for j is equal to 1 I is equal to 1 we do get it u02 minus 4 u12 plus u22 is equal to minus u11 minus u13. So, these 2 points are our boundary points, and remaining right hand side this point we are having is u11, that is initial guess is 0, u02 means is your this point which is 100, and u13 is this point which is 0. So, you are getting is minus 100, and this internal this initial guess u11 was 0. So, what I would get the equation would be actually right hand side would be 100, but let us first write the second equation as such, that is for the point u22. So, for the point u22 we would get u12 minus 4 u22 plus u32 is equal to minus u21 minus u23. u23 and u32 they are boundary points, one is 0 another is 100, and initial guess u21 is 0. So, for here for the first equation, since our initial guess is 0, u02 is 100 and u13 is 0, I do get the first equation as minus 4 u12 plus u22 is equal to minus 100. Similarly, from the second equation again I would get u12 minus 4 u22 is equal to minus 100. So, again we have got, because the two equations 2 unknowns and 2 equations, that is because we are having only 2 internal points. Solve the system of equations, we do get u12 as 100 by 3 and u22 as also as 100 by 3. So, finally, what we have got our first approximation in this case as u11 is same as u21 is 66.66 and u12 and u22 as the first approximation as 33.33. Now, move to the, now alternate the direction, that is now move to the column 1 using this as the now first approximation. So, we move to the second approximation. The first approximation is u11 and u21 as 66.66 are 200 by 3, u12 and u22 as 100 by 3. Move to the first column, because we will now move to the column first fixed column. In the first column we do have 2 internal points. So, again we will start with the first point j is equal to 1. What we would get is u10 minus 4 u11 plus u12, this is the points, is equal to minus u01 minus u21. So, this is the point you are getting over here. So, right hand side we would write the first guess and the second, and the left hand side we want the second approximation. the boundary points u10 and u01, u10 and u01 both are 100. Now, first approximation we have got u21 as 200 by 3. So, we are getting is minus 200 by 3. So, this is for j is equal to 1. Now, we will move to the j is equal to 2, that is u12 point. What we would get? We would get u11 minus 4 u12 plus u13 is equal to minus u02 and minus u22. Again u02 and u13, this is u02 and u13, they are the boundary points. So, we are not keeping anything. u22 is the internal point, for this the first approximation, and the left hand side we want the second approximation. u10, now come to this our first equation, u10 and u01, u10 and u01 both are 100. So, we would get it here this side minus 200 minus u21 at first approximation, that is minus, that is 200 by 3. So, minus 200 by 3, what we would get is minus 4 u11 plus u21 is equal to minus 800 by 3. Similarly, here u13 is this 0 and your u02 is 100. So, we will get minus 100 and u22 at 1 is 100 by 3. So, what we would get, the second one is u11 minus 4 u12 is minus 100 by 3, that is minus 400 by 3. Again, because of two internal points only, we will get a system of two equations in two unknowns, solve it and we would get the solution as u11 as 80 and u12 as 160 by 3 or 53.33. Now, move to the second column. Second column we do again have two internal points u21 and u22. So, first start with first internal point, we are moving in the column manner. So, we would get u20 minus 4 u21 plus u22 is equal to minus u11 minus u31. Now, u31 and u20, these are your boundary points, and u11 on the right hand side, this is from the first approximation. Similarly, if I move to the second point u22, what I would get, because we are moving in the column direction, it should be u21 minus 4 u22 plus u23 is equal to minus u12 minus u32. u32 and u23, they are boundary points. Moreover, this right hand side u12 is the point that is for the first approximation, and here we would get on the left hand side the second approximation. Now, if I substitute it, boundary points here in the first one are giving you u20 and u31. u20 means this point and u31 is this one, both are 100. So, we are getting is minus 200 and the first approximation u11 at 1 is 200 by 3. So, what we would be getting is minus 4 u21 plus u22 is equal to minus 200 by 3, that is minus 800 by 3. Similarly, if I move to u23 and u32, u23 would be the point which is 100 and u32 is the point which is 0. So, we would get is minus 100 and the first approximation for u21 is 100 by 3. So, we would get the second equation as u21 minus 4 u22 is equal to minus 400 by 3. Again, we have got 2 points. So, 2 equations in 2 unknowns, solution will get u21 as 80 and u22 as 53.33. So, what we have got the second approximation? Second approximation we have got as u11 and u21 both as 80 and u12 and u22 both as 53. So, we had got that is. Now, the same example we have solved with the 2 methods. First we have done in the last lecture as the Gauss-Seidel method, then we have solved it using this ADI method with the 2 initial guesses. One guess we had started as 100 and 100, another guess we had started with 0 and 0, and moreover because this was a simple problem we could actually make it as a very simple equation. So, we had also find out after this discretization the Gauss elimination method, the exact solution of those system of equations, which initially we had got before applying this one or Gauss-Seidel one. So, let us see, compare all these methods what the answer we have got. With the ADI method in the second approximation using initial guess as 100, we have got U11 and U21 both as 91.11, U12 and U22 both as 64.44. When I have changed my initial guess from 100 to 0, we had reached to this U11 and U21 as 80, U12 and U22 as 53.33. In the Gauss-Seidel method in the last lecture, we have got the solutions U11 as your 93.74, U21 as 65.62, U12 as 90.62 and U22 as 64.06. While as the exact solution, this was starting with initial guess as 100, 100, 100 for all. If to remember, that is, we have done this Gauss elimination method, that the exact solution of the system of equations after the changing our partial derivatives to the difference quotient, we have got the just algebraic equations for the 4 unknowns and 4 equations that we had solved, and we got it, that is the solution was U11, U21 was 87.5, U21 was your 62.5, U12 was 87.5 and U22 was 62.5. Now, you see of course, the solutions are coming as different. Here in ADI method we are getting is in one solutions we are getting in the row manner, they are equal for the first row and they are equal for the second row. In the Gauss-Seidel method we are getting is they are coming as the column manner, that the first column the points we are getting it rather they are not equal, they are all the 4 points are different, while as in the exact solution we have got that in the column manner, that is U11 and U12 are same and U21 and U22 are same. Of course, with such a smaller problem and with only 2 steps, it is not easy to check about the convergence in more general, but still we do have an idea that these methods, iterative methods, they would depend upon what is initial guess. So, we have to make a very cautious initial guess at each point. Moreover, the problem is that my solution is moving depending on the method also. The Gauss-Seidel method we are getting different way, in the ADI method we are getting different manner. So, we have to choose this method also very cautiously, that is in which problem we are talking about here only actually one problem, that is the Dirichlet problem for the Laplace equation we have talked about. We had find it out, that is different methods are giving our different approximations. If I solve this same problem, you can do this as an exercise, usual method, that is we have done it the Dirichlet problem for the Laplace equation using the Fourier method. There of course, you will get the Fourier series, and that Fourier series again to find out the solution, that is approximate that at each point, that is your temperature at each mesh point, if you have to do it, that is you have to find out rather at the internal points, that is Fourier series you have to approximate, or you have to find out the sum of the series. So, that there also the approximation, but the Fourier series you can use any of those known softwares or any of the series. So, you can find out that approximate value over there, and then from there you can compare these approximations and see, because this is a very simple example. So, you can do this exercise by yourself, see which of these 3 solutions is more near to the Fourier approximation, because Fourier approximation first we have got using it analytically, and then the solution, final solution we had approximated. Here what we are doing is we are solving the problem numerically, that is we are actually modeling the problem rather than analytical solution, we are finding out numerical solution. So, see which one is better one, or which one is approximating it better level. At the second approximation itself, you can go ahead with this exercise doing, you can use your calculators or computers, you can make the programs and can go on checking it, that is where they are converging, at the converging stage whether they are giving you same solutions or similar kind of solution with less actual Fourier solutions, or what you could check it, that is the Gauss elimination method, that is the exact solution which I had got over here. This is a little bit more near to the Fourier series approximation than these ones. So, these can move, if I can, these can also converge to this kind of solution or to the Fourier solution if I had gone with more iterations. So, that process you can do by yourself, because this step is very easy, you can just go on using the calculators, or if you are little bit more interested, you can make a computer program for these methods, because they are very simple, solving algebraic equations, and you can check, that is where they are converging, how much time they are taking, and which method you would prefer. All these things you can do at the first stage, that is just to get understanding. Certainly there are many people who have worked on these ones, and they had suggested in which kind of equations, which kind of method is more suitable, with what kind of boundary conditions, which kind of method is more suitable. So, there are lot of numerical methods available in the your textbooks, as well as you can find it out more for your proper solution of any equation. This method, numerical method, I had discussed only for the Laplace equation. I have not gone for the Poisson equation. The Poisson equation, the difference would be, that is the right hand side, when I was getting it, say if I am talking about this first equation which we have got, that is 4 equations and 4 unknowns, we have got on the right hand side all the times 0. Right hand side is 0, there what we would get is h square f x y, that is at all those mesh points. X y point means is, that is whatever the mesh point you are getting is. So, if in this same problem I am talking about, the first mesh point was our u11, that is at the point 4 4, that is x was 4, y was 4. So, we find out whatever the function f x y is given at x is equal to 4 and y is equal to 4, what will be the value of that function f x y. Suppose f x y is x square, then the value of the f x y at x is equal to 4 and y is equal to 4 would be simply 4 square, that is your 16. So, rather than having on the right hand side as 0 in the first equation, you would get 16 into h square. Now, h was your also 4, so you would get it 16 into 16, that is 256. So, rather than getting the right hand side as 0, you would get it the right hand side as some numbers, and then using the boundary conditions, since you have got all the right hand side as the negatives, the minus 200, if you do remember your Gauss elimination in this example, minus 200 and minus 100, you would get it actually 256 minus 200, that is you would get 56 and so on. So, that is you would be getting some right hand side different column. The method would remain same, either you have to use, and the simple one here, if you do, you can find out the Gauss elimination method or Gauss seidel or ADI. Certainly Gauss elimination directly we are not using, because it takes too much time. You can check it with yourself also, that this is Gauss elimination. Actually what it does is that it changes your 0 entries to your non-zero entries to 0 entries in a you could say is in a fixed manner, or in a fixed manner, that is in the first it is going in the first column, then the second column, like that one, and then you are getting a solution. Since our matrix, coefficient matrix, comes out to be sparse, what it is doing is, it is never guaranteeing, that is in 0 entry it will not make non-zero. This has never been guaranteed in Gauss elimination. So, what it will do is, it will do again 0 entries to non-zero, and then 0 non-zero, and then for again you have to make it 0 entries. So, it would take too much time, that is why this has not been preferred method. Of course, it gives the exact solution for the coefficient matrix, or for that your algebraic equations. So, we are going to use this any of these methods, they are taking less of your computation time, but here you have to be very cautious about, or very judicious what this initial guess must be, and which method you should use in which kind of boundary condition and which kind of equations. So, we had learned about this numerical method to solve this partial differential equations. That is all for today's lecture, and we would be ending up here our this course for the differential equations on undergraduate one. We have learned in the partial differential equations linear equations, the first order equations, the second order equations, and in the second order equations we have learned about certain practical problems, that is the heat equation and the wave equations. We solve them using the analytical methods, say as the Fourier methods, and then we had done some insight into the numerical methods. So, this is what the partial differential equations. In ordinary differential equations, certainly we had learned many analytical methods for different kind of differential equations. So, thank you.